When a celestial body rotates, of course, its gravitational field also rotates, which we call the rotating gravitational field. And when the Sun attracts the Earth with its gravitational force and thus holds it, and rotates at the same time, the Earth is accelerated by the Sun's gravitational field in the direction of rotation. It's like an electric motor whose stator generates a rotating magnetic field that drives the rotor. We refer to this as the rotary motor effect. So the Earth and all planets are driven by the Sun's gravitational field and thus they revolve around the Sun. This is a simple and unambiguous physical phenomenon, but has not yet been recognized by anyone. But why? Because from previous physics the speed of the planets from the Sun would be accelerated to infinity. Now we know from new knowledge of inertia that the speed of an accelerated body is limited and can be calculated with a simple equation. The driving force from the gravitational field is precisely the force with which the Sun holds the Earth, i.e. the solar gravitational force. That means, the strength of the gravitational field is the same as that of the gravitation itself. If necessary, we denote the gravitational field force with G** in order to distinguish it from the gravitational force G. So they have the same strength. Therefore, the maximum orbital speed of a planet accelerated by the Sun can be calculated as follows. This is exactly the speed with which a body can run forever around a central body. We call it orbital velocity, which is denoted as follows. So the driven body is accelerated by the gravitational field of another body exactly to the speed it needs to be able to run around the driving body forever. This means that the resulting centrifugal force of the driven body exactly compensates for the attraction of the driving body. This fact suggests that all planets in the solar system are driven by the Sun's gravitational field. With this we have solved a huge problem in physics. Why do all planets revolve around the Sun at all? Although, that's just a foretaste of the real physics. This solves the mystery of why a planet orbits the Sun the faster the closer it is to it. This phenomenon will be explained in detail later. This saves the space an adventurous maneuver, namely to curve it. However, there is one condition: that a body is accelerated by the gravitational field of a central body to its orbital speed. The central body must rotate, although its angular speed must be at least as fast as that of the rotation of the driven one. The reason is because the speed of a driven body cannot be faster than that of the driving body. As for example, the speed of a trailer cannot be faster than that of its driving tractor. This means that the acceleration or the force also has its own speed of propagation, which also limits the speed of a driven body. If a planet is at point A and *its orbital velocity is lower than its orbital velocity, it is accelerated by the Sun's gravitational field to exactly its orbital velocity, at point A*. The red curve shows the possible orbital angular velocity of a planet. For example, if the angular orbital velocity of a planet is the same as the angular velocity of rotation of the Sun, then the planet is exactly in geostationary orbit. There the orbital velocity curve crosses with the line of the solar angular velocity at point C. If a planet is at point B, for example, which is below geostationary orbit, it can be accelerated to a maximum of point B*, at which its angular velocity is the same as that of the Sun. That is, its speed is less than the orbital angular velocity it takes to compete against the Sun's gravitational pull. Then he will fall in the Sun. If a body is accelerated to its orbital velocity by a rotating gravitational field, then logically the speed of a body is also slowed down if it crosses the gravitational field faster than its orbital velocity. For example, if a planet, at point D, runs faster than its orbital velocity, its speed is also slowed down to the orbital velocity, at point D*. The physical explanation for this phenomenon. Because the inertial force of a body is always the same as the respective external force, if it does not exceed its maximum. If a planet moves around the Sun with velocity v, which is faster than its orbital velocity v orbital, the force acting on it, which is equal to the gravitation of the Sun, is as follows. This is equal to the actual inertial acceleration. This means that the body with inertia only remains at its orbital velocity. And the resulting remaining part is not guaranteed by inertia, and defenselessly delivered to the gravitational field and thereby slowed down, then the planet will ultimately only run around the Sun at orbital velocity. The mathematical explanation. When calculating the equation of inertia, did we already mention why, according to this equation, if the initial speed v0 is greater than the target speed, the speed of an accelerated body is reduced to that is the orbital velocity. So the speed of a body circling around a central body is brought exactly to its orbital velocity by the influence of the gravitational field of the central body, although it is independent of the initial speed of the body. Unless it is too close to the central body, it will fall into it. From this equation we also see that the speed of a driven body is fundamentally independent of its mass. This is actually already clear, because the force of the gravitational field is identical to that of gravity. We know the story of feather and hammer. In free fall, the feather and hammer land on the ground at the same time. In addition, we can imagine that the orbit of a planet around the Sun would have to be completely round, if it were not disturbed by other forces. The fact that a rotating gravitational field has a driving and braking effect on the body located in this field only applies to the tangential direction. That is, it only applies when a body cuts through the gravitational field. The rotational movement of a body is also influenced by the gravitational field of another body. When a body rotates in a gravitational field, each point of mass in it cuts the gravitational line at a different angle. Therefore, each point in the body is slowed down differently. For example, any point mass p is influenced by a braking force. If we consider a ring of point mass with radius r, the braking force that the ring experiences is the same as because this braking force only depends on the mass of the ring and not on its radius, the total braking force of the body is equal to the sum of all rings. The braking acceleration is the same as follows. This means that a body can rotate in the gravitational field of another body. It needs its own rotational force, which must be greater than 2/pi times the gravitational field of the other. Conclusion: if a body, like a planet, is in the gravitational field of a central body, like the Sun, it will be accelerated by this gravitational field to its orbital speed. If it moves around the central body at a speed that is faster than its orbital speed, it will be brake to its orbital speed. And so that it can rotate in this gravitational field, it needs its own rotational force, the strength of which must be 2/pi times greater than that of this gravitational field. Thank you very much for your attention. See you next time.